Good afternoon. Thank you for the opportunity to make this talk. You know, a few days ago I got a mail saying that I was going to talk to a group of experts in NILM, and I should avoid talking about introductions or making long introductions. So I decided to start with the end of my talk. I will go directly to the architecture we are proposing. Our architecture is a multi-agent architecture. It is made of two sorts of agents. One agent that is able to detect load events, and another agent that's able to identify the loads. So the load event detection agent is basically responsible for pre-processing, feature extraction, and detection. The pre-processing consists of filtering, zero crossing detection, and so on. Feature extraction depends a lot of the specific agent we are using. It can decide to do power calculations, or it can be based on wavelet or on vectorization. That's a technique we are developing. And the detection part means that if the feature extraction gives a certain number, a certain value, then we can say that it is an event or it's not. Actually, we say if it's likely to be an event or not. The result of provided by a load event detection agent is three. We have first an indication of a probable event. So we just say at this moment in time there's likely to be an event. There is a transition window, which is a window in time in which the likely event occurred, and is finally a certainty level. So how certain that agent is that an event occurred. Then we move to the second sort of agents. They are, again, feature extraction and classification. It's a different type of feature extraction this time, because now we are interested in classifying the load. So feature extraction in this case may be the power envelope, may be the VI curve, and so on. And the classification can be something like the K nearest neighbors, or the ensemble, or the SVM. The result of this sort of agent is an indication of a probable load type, and again a certainty level. As we put both sorts of agents into our architecture, we arrive at this diagram. So starting on the left, you can see first that we have sensors, 4 sensors for current, 3 sensors for voltage. They deposit samples in a circular buffer. We are using a sample rate of 15,360 Hertz. In Brazil, where I come from, we use a 60 Hertz mains, and we wanted to have 256 samples per cycle. So we arrived at this frequency, 15,360. These are deposited in a circular buffer that holds possibly about 10 seconds of data, which is the window we need to make our analysis. Then we come in blue to the event detection agents. Each one of them will provide those 3 results, indicating a probable event and a certainty level. And then this composition block will decide if there is a likelihood of an event or not, and will inform the signature analysis agents, which are these in orange. And they stay sleeping most of the time, and they only wake up when one of the blue agents informs them there's some work to do. So again, several of these agents work concurrently, and they vote, and this other block composition will decide which sort of load had an event. An event is something like turning on or turning off, or in a multi-state load may be a change of state. Whenever I see a signature that's not in my database, I activate the training module, and the training module will extract the features and will put more information into the load database. At the end, what I hope to do is to have a disaggregation of the input I had, and what I want to present to the user is just an event database, which is just a list of times, loads, so the load identification, and the load event that occurred. So I would say the washer machine went on at that time and then went off at that other time. We did several experiments with this architecture. So first we started analyzing each one of the agents by itself to later on combine them and see if our results improve it. So for the load event detection agents, we used a discrete wavelet transform agent, a Kalman filter, derivatives, which are just measuring the change from one cycle to the other, a half-cycle active power analysis. This means that every half cycle of our mains, we are calculating the active power, the apparent power, and the reactive power, thank you. And after that, why did we decide to use a half cycle? Because many of the loads we were working on were asymmetric. So one semi-cycle was different from the other, so we decided to do the analysis semi-cycle by semi-cycle. And finally, the vectorization technique that we are developing, which just transforms a transition from one power level to another power level into a multidimensional vector where each component is a complex number. And then by comparing the vectors, we can see if an event occurred or not. So we have here 5 load event detection agents, which were the blue ones in my block diagram. Now I move to my signature analysis agents, which are the orange ones in my block diagram. And here we have a discrete Fourier transform. We have the same one, discrete Fourier transform with exponential damping. We have VI trajectories, which will be presented in the next talk. We have a wavelet, and we have the power envelope. I saw in the previous presentations a lot of work on power envelope, but these were power envelopes taking over a long period of time, maybe 1 hour. Our power envelope is taken during a transition of a few cycles or maybe 1 second long. We divided the power envelope into 4 classes. The first one we call it negative exponential, the other one is spike, then step, and finally grow. And the second part of the signature analysis agents are the classifiers. So as I said, we are using the k nearest neighbors, the ensemble, the SVM, and a decision tree. We were working basically with two data sets, the cool data set that's well known, and a data set we are developing ourselves. The data set will be presented tomorrow in the afternoon. It will also be presented in the poster section if you want to hear about it, and in the lightning talk just after this session. By using these 2 data sets, we compared all these agents. So first we compared the load event detection agents. Here we have a list of the agents, and then the amount, how often are they able to detect an on event or an off event, and the number of false positives. So you can see by this table that Kalman filtering and the half-cycle active power, they were the best, had the best results for the cool database. And by combining these two into the architecture we proposed, then we get a better result than each one alone. So we got 100% detection for the on and 95% detection for the off, and no false positive. We did the same for our data set when we have a single load, and again we have a better result than each one by itself. And finally we compare them when we have multiple loads. So our data set also has multiple loads in a single waveform, and then again we have a better result than each one individually. For the other agents, the load event classification, we get this sort of agents. Their results, the best result is when the classification machine is the ensemble. We got 90.5% accuracy and 87.5% accuracy for the exponential DFT and for the wavelet. And by combining both of them, we got a higher accuracy of 93%. So this shows that by combining the results of individual agents, we usually get better results. We are still working on analyzing what would be the best combination of agents so to have the best coverage. It's not always the best idea just to get two agents that by themselves have good results. Sometimes we have agents that have not so good results when they are looked individually, but they have very good results when they are combined. Well, to conclude the first part of my talk, I would resume that I would summarize that we proposed a multi-agent architecture, and we can see so far that there are benefits in performance when we do this combination of multiple agents. Complementary agents are the best way to go. And it's still ongoing work, so our group has still 1 year ahead in the project we are working right now. I would like to take a few minutes to present the team that's working. So you see here a list of faculty and students. Here you see Professor Podker, she's from the area of power electronics, and recently published a book on soft commutation. Here is myself. Professor Eric is from the area of control. Professor Zorowski and Lazzaretti are from the area of machine learning. And Professor Linhares is from the area of software development. Then we have our students, two grad students. Bruna is sitting right here. She will be doing the next talk, and 4 undergrad students. We all come from a university in the south of Brazil, in a state called Paraná. So up there you see the name of the university, which would translate to English into the Federal Technological University of the state of Paraná. And it has 13 campuses all over the state. And this is the main building, the administrative building in the capital city of Curitiba. Thank you very much.